All right, hello. It's me, Mr. Smith. I'm not here right now. I'm on Year 10 camp, presumably having the best time of my entire life. Um, but I'm recording this so that we've got something that we can look back over and so that we don't fall behind. Today we're going to be looking at graphs of factorized cubics, which is chapter 6F, and we'll also look at chapter 6G, which is inequalities with cubics. These two are pretty related, so I think we'll be good to get through them in one single lesson. Let's get into it. Okay, so we've looked a lot at how to turn our cubics into factorized form. Remember, if we're turning it into factorized form, that means we're taking our cubic polynomial, and we're turning it into something that looks like a whole bunch of brackets multiplying. And some of the ways that we've done this using long division, we've done this using equating coefficients. Sometimes we get lucky and we can just do it by taking out common factors. Either way, we know how to do it. Once we know how to do it, well, the reason that we do it is so that we can plot. You might remember from our study of quadratics, when we have factorized form, that makes it really easy for us to plot things because it gives us the x-intercepts. If you have your factorized cubic, you set it equal to 0 and you solve for x, that gives you the x-intercepts. You can solve by using that null factor law. And let's see that in action right now. So I've got y equals x minus 1 times x plus 1 times x minus 2. What we're going to do is we're going to set that equal to 0. So we're going to say 0 equals x minus 1, x plus 1, x minus 2. And then we're going to use our null factor law. Hopefully you didn't hear that. X minus 1 equals 0. So x has got to be 1. This one here is going to give us x plus 1 equals 0. So x has got to be negative 1. And this one here is going to give us x minus 2 is 0. X has got to be positive 2. Cool. And so now we've got these. We can put it on a graph. So here's our x equals positive 1. Here's our x equals negative 1. I'll just label these minus 1, 1, and here's 1 at 2. Those are my three x-intercepts. So I'm going to draw in blue. I could have a cubic that looks like this. Yay! But with this, I could just as easily have a cubic that does this, couldn't I? Both the blue cubic that I've drawn and the green cubic that I've drawn, they both have x-intercepts at x equals 1, x equals negative 1, and x equals 2. We need some more information, and that extra little bit of information is going to come from our y-intercept. So just like every other time you've ever found the y-intercept, we're just going to do that by making x equals 0 and solve for y. So I'm going to take this thing here, I'll draw a little arrow so we can see where we're going. I've taken the equation, I'm going to say y equals, I'm going to sub in x equals 0. So 0 minus 1, 0 plus 1, 0 minus 2. And then we're going to get minus 1 times negative 2, which is going to give us positive 2. So that means that we're going to have the blue one. I'll just erase this green because that's not good for us. And now we've made a nice little graph of our cubic. Hooray! And I'll just label this because it's important to label your x and y intercepts. You might notice that we don't have the turning points. So you can also use the sign of the x cubed term. If you have a expanded form, then you can look at the x cubed and you can use that to determine whether your cubic is going to be like this or it's going to be flipped, just like you can with quadratics. One thing that's different between cubics and quadratics, for now at least, one thing that's different is we don't know the turning points, right? You can see we've got a turning point. We've got a turning point happening here, one there, and another turning point happening down there. We don't know where those are at the moment. We will see how to find those later on. So when we have these cubics, they don't always have turning points. We saw on Monday that sometimes we have cubics that have a point of inflection, right? That point where the gradient becomes 0 and then it keeps going in the same direction it was before. But if we have more than one x-intercept, then we will have turning points. If you have one x-intercept, you will have a point of inflection. If you have two x-intercepts or three x-intercepts, then you will have turning points, no point of inflection there. When we get to Unit 2, we'll start to look at calculus, and when we're doing calculus, you will be able to find the coordinates of these turning points. You will need to find the coordinates of these turning points on cubics. But for our current SAC and our current exam, unless your turning point is on the x-axis, in which case it's probably pretty easy to see, then it will be, you won't need to find the coordinates of the any turning points. Okay, so in that one x-intercept case, we have two potential equations. One of the equation is like we saw on Monday, right? The y equals a x minus h cubed plus k, and we find our stationary point at a point of inflection at hk. Otherwise, we'll have our equation looking like a linear term times a quadratic term, right? If we look at this second one, you can see we've got a times x minus h, that's a linear term, times px squared plus qx plus r, that's a quadratic term. And in this case, we can't factorize that quadratic. If we can't factorize that quadratic, then we're going to have our one x-intercept case. These are going to sometimes, not always, but sometimes have a point of inflection, a stationary point of inflection. The a x minus h cubed plus k, the one we looked at on Monday, that will have a stationary point of inflection. The other one, it might not. It really depends on what those individual numbers are. If you're going to do these, generally you need to use a CAS. There's not much of a way around it. You can try to plot it by like subbing in points and things, but it's pretty hard to do without a CAS. I think just use the CAS. So let's do one real quick. I'm going to sketch x minus 1 times x squared plus 2x plus 3. So if we look at this, well, the first one, the x minus 1, that's clearly a linear term. The second one, x squared plus 2x plus 3. Well, can I factorize that? Are there any factors of positive 3 that add to give me positive 2? Well, no, there's not. I can't do that. So this is going to be something that we're going to have to try and either use a CAS to sketch, and I'm sure we can. I'm sure you know how to do that. I hope you do, because I'm not here to show you and I can't record it, but that's okay. We can still find the other part. So we can still say, all right, let's find our x-intercepts. Our x-intercepts we're going to have make y equals 0. So x minus 1 times x squared plus 2x plus 3. So x has got to be 1, right? And that comes from the first thing. That second term, that quadratic term, because we can't factorize that, right? Because we can't factorize that, that thing is never going to be, that's never going to be equal to 0. So we can't get another x-intercept out of it. So we just have that one x-intercept at x equals 1. We should probably find any y-intercepts as well. Y-intercepts are good too. So I'm going to say for y-intercepts we make x equals 0. So y equals 0 minus 1 times 0 plus 2 times 0 plus 3. So we get y is negative 3. And so we can kind of start to put something together. We've got this x-intercept at 1, this y-intercept at negative 3, and we might get something like this. If you want to double check that, use the CAS calculator to sketch it. That is by far the best way to do that. Okay, if we have two x-intercepts, we will have a turning point on the x-axis. This is what I was saying before, when there's one circumstance where you need to be able to learn to label the turning point in this current unit 1, and that's when we have our cubics where we have a turning point on the x-axis. And so when we have that, we'll have a linear term and a quadratic term. But the quadratic term is something that we can factorize nicely. You can see there we've got x minus a, that's our linear term, and x minus b squared, that's our quadratic term. But because that quadratic term is nice and easily solvable to be equal to 0, we can plot that, no worries, no whackers. When we do this, we're going to have a turning point at x equals b, which I just said there. So let's have a look at this. We've got y equals x plus 1 times x minus 1 squared. So in this case, well, we're going to have a normal x-intercept at x equals -1. That's from our x plus 1 term. And then we're going to have a turning point at x equals 1. Right? Because with that turning point, because this second bracket is squared, that's the key to it. Because this second bracket is squared, that means that we're going to have a turning point there. Okay, and the other thing we're going to need is our y-intercept. That way we can see what goes where. So we're going to say, all right, y equals sub in x equals 0, 0 plus 1 times 0 minus 1 squared. Well, it's going to be 1 times 1, which is 1. Y is 1. Okay, so y is 1, x is 1, and x is -1. Let's put it all together. Here's my little poorly drawn graph. There's 1, there's -1, and then we've got y is 1 up here. And so we know we're going to have a normal x-intercept at this intercept at -1. We're going to go up through our y-intercept at 1, and we're going to have a turning point at x equals +1. It's going to look like this. And in this case, that's it. We can get the shape. We can get the x-intercepts and the y-intercepts, and we use those to tell us the shape. All right, sign diagrams. I left this in because I thought that some of you might like to see it anyway, just to get an idea of what it is. This is basically, the textbook loves these. I think they're useless. Every other maths teacher that I talk to thinks they're useless. Textbook loves them. If there's a question about them, you can probably just skip it, honestly. Sign diagrams are just little diagrams that tell you whether the graph is positive or negative. But if you find your x and y intercepts and you connect the dots, then you don't need to use these. If you see a question about it, skip it. There won't be any in your SACs. There won't be any in your exams in year 11 or in year 12. But if you want to read about it, go for your life. Don't let me stop you. Okay, so now we're going to see an example of all of this being put together into one. And we're going to do that by sketching this cubic that we've got here. And the first thing you might notice is that this is not in factorized form. So that's our first job. We've got to factorize it. If we're going to factorize it, this is when we use the, sorry, my cat just jumped. This is when we use the factor theorem. So I'm going to call this thing f of x, and then we need to pick numbers, substitute them in, and see if it equals 0. If it does equal 0, then that number that we put in, x minus that number, will be a factor. So I look at this thing here, and I see a bit of symmetry, right? I see -6 and -6. I am thinking, hey, maybe 1 is going to work. And the reason that I'm thinking that is because I made the question. So let's see f of 1. Let's see what happens. We get 1 cubed minus 6 times 1 plus 11 times 1 minus 6. Well, 1 cubed is 1. Oh, that should be 6 minus 1 squared. 1 minus 6 plus 11 minus 6. 1 minus 6 is minus 5, plus 11 is +6, minus 6 is 0. Wow, so cool, so insightful. I can't draw a 0 to save my life. So we now know that x minus 1 is a factor, right? That's what the factor theorem tells us. If you substitute it in and it's equal to 0, then x minus that thing is a factor. So we can say that f of x is going to be equal to x minus 1. That's our linear term. And then it's going to be times, if we times a linear thing by some random quadratic, we don't know what this quadratic is, I'm just going to call it ax squared plus bx plus c, so completely anonymous quadratic. We know that if we multiply a linear by a quadratic, we'll get up to a cubic, which is good, because that's what we expect. And so now I'm going to expand this thing, and I'm just going to say equals x cubed minus 6x squared plus 11x minus 6. And now I'm going to expand this left-hand side and set my coefficients equal. I'm using equating coefficients to do this. I choose equating coefficients because I like it. If you like long division, go ahead and do long division. Just keep it to yourself. I don't want to hear about it. I find long division very tedious, and I find it very easy for me to make mistakes. So this is what I use. I use this one because it works best for me. If you find that long division works best for you, then go ahead, use that. So right now I'm just expanding my left-hand side. And then I'm going to match up my coefficients on the left-hand side with my coefficient on the right-hand side. So minus bx minus c, and that's going to be equal to that same stuff that we've got on the right-hand side. X cubed minus 6x squared plus 11x minus 6. Okay, cool. So I look on my left-hand side, I can see, hey, there's only one x cubed term there, right? It's only the ax cubed. And on the right-hand side, well, there's only that x cubed. So I can just say that 1x cubed on the right-hand side. So I'm going to say, well, that tells me that the amount of x cubes on the left-hand side, which is a of them, has to be the same as the amount of x cubes on the right-hand side, which is one of them. So a is 1. Next, I'm going to go down to the constant terms, right? And you might remember constant terms, those are x to the power of 0. And while for x to the power of 0, we're going to have on the left-hand side, it's just negative c. That's all the constant terms on the left-hand side. And then on the right-hand side is negative 6. And would you look at that, we get c is 6. All right, very nice. And for the last one, I can pick between my quadratic terms, the x squared terms, or the linear terms. I'm going to pick the linear terms because in the first two takes of this, I use the quadratic terms. So let's vary it up a little bit. So for the linear term, the x to the power of 1, on the left-hand side we've got this cx term here and this minus bx term here. So we're going to have c subtract b, and then on the right-hand side, our quadratic, the linear term is positive 11. So c minus b has to be 11. This is my linear terms that I'm putting together. We already know that c is 6. So we can say that 6 minus b is 11. So then if we solve this, 6 take away what gets you to 11, while the what has to be negative 5. b is negative 5. So my quadratic portion of f of x therefore has to be, we'll still have our ax squared, sorry, our x minus 1, apologies, I don't know where ax squared came from. So now I can fill in the a, the b, and the c that I just found. So it's going to be 1x squared. Well, we don't really need to write the 1, do we? We can just skip that. 1x squared minus 5x, that's our b, plus 6. And now let's have a ponder to ourselves. Are there factors of positive 6 in this quadratic part of my cubic? In this quadratic part of my cubic, can I factorize this? Are there factors of positive 6 that add to give me negative 5? Well, yeah, there are. There's negative 2 and negative 3. Negative 2 times negative 3 is 5. Negative 2 plus negative, oh my god, negative 2 times negative 3 is 6. Negative 2 plus negative 3 is 5. So we can factorize this, therefore, into x minus 1, x minus 2, x minus 3. And finish that bracket. And now, finally, we've got our factorized form. Finally, we can find our solutions. We can find our x-intercepts. So I'm going to set this thing equal to 0, equals 0. We're going to have 3 x-intercepts. X equals 1, x equals 2, x equals 3. How easy was that? It was long. There's a lot to it. I 100% agree with you on that one, because I'm assuming that's what you're thinking right now. But once you get used to this process, it's not too hard to put it all together. All of this stuff we're seeing here, we've done this before. All we're doing now is we're putting it onto a graph. And we've put things onto graphs before. We've done that heaps. So we're going to have x equals 1, x equals 2, and x equals 3. 1, 2, 3. Those are going to be our x-intercepts. That's what we found before. To find the overall shape, we've got two choices. First choice, we can find the y-intercept. Remember, y-intercept, we make x equals 0. So we can go, all right, y equals f of, oh, sorry, I'll do it as, I'll keep my f of x notation, why not? F of x, so we're making x equals 0. Oh my giddy aunt, Mr. Smith still has holiday brain, because unfortunately he's doing this on the holidays. So we're going to say f of 0, we're making x equals 0, is going to be 0 cubed minus 6 times 0 squared plus 11 times 0 subtract 6. Well, everything is going to be dropping out except for that minus 6. So equals negative 6. That's it. So there it is there. There's my minus 6. Now we can join the dots. Bop, bop, bop. Connect all the dots. There it is. Hooray, that's my f of x. That's my function completely graphed. The other way that I was mentioning before that you could have found the y-intercept, that you could have found the shape, is you look at the sign of the x cubed. If the x cubed is positive, then your overall cubic will be positive. If the x cubed is negative, then your overall cubic will be negative. Just like with quadratics, when we're finding the minimum or the maximum, we look at the sign of the highest power term. That didn't make sense. If you didn't remember doing that before, that's fine. I like finding the y-intercept better because I like connecting the dots. Sometimes I wish I was still in grade 1. All right. Okay, so we've got one last thing that we need to look at for today, and that's this idea of cubic inequalities. And really, this is just a little tack on to the last idea that we've been looking about where we've been sketching. We're just going to use sketches to solve cubic inequalities. It's just like when we did this with quadratics, right? We find where it crosses the x-axis, and then we fill in the areas that we need. I think that factorizing is essential. This sign diagram might be helpful here, but don't get hung up on it. It's still a sign diagram at the end of the day. It's not that useful. So let's just get straight into it. We're going to solve where this thing here, x minus 1 times x minus 2 times x plus 3, solve where that is less than 0. So first thing we're going to do, we're going to sketch this. All right, here it is. And we're going to have x-intercepts at positive 1, positive 2, and negative 3. Minus 3, 1, and 2. And let's find that y-intercept as well. That y-intercept is going to happen where x is 0. So 0 minus 1 times 0 minus 2 times 0 plus 3. If we put all these together, we're going to get 0 minus 1 is negative 1 times negative 2 times positive 3. It's going to give us 6. There it is up here at 6. That's about 6, I say it is. And now we're going to connect the dots. Yay, my favorite part. Connect the dots. There it is. Okay, and so we want for this thing, it demands to know of us when this quadratic that we've sketched, when this cubic that we've sketched, when it is less than 0. Well, to do that, all we need to do is look. Where's this thing less than 0? Well, it's less than 0 over here. We're looking for when we've got y values that are less than 0. What's going to happen over in this section here and this section here. And then the last thing we need to do, you can see between when we're less than negative 3 and between 1 and 2. And now all we need to do is write that down. That's not too hard, I think. So we're going to say x is less than negative 3. That's our left-hand side, in union with 1 is less than x is less than 2. That's it. That's all you got to do. See one more. This time it's not factorized, but actually we've done this one before, right? This is one that this is the same quadratic that we saw before. We're still looking, this time we're looking for when it's positive. Let's bring back our sketch. So you might remember, you might not, I barely remember, but the x-intercepts were at 1, 2, and 3. And what was the y-intercept again for this one? It was negative 6, that's right. So down here at negative 6, 1, 2, 3. Going to continue to connect the dots. Boop, boop, boop. Not the greatest graph in the world, but that's fine. And we want when this thing is positive, Well, it's going to be in this region here between x equals 1 and x equals 2. And then as soon as we get past positive 3. And now we just need to write that down in notation. So we can, this time I'm going to use the brackets notation. Do I want a square bracket here? No, I don't, because we're not including when x equals 0. That's going to be from 1 through to 2 in union with 3 through to positive infinity. And that's it. So this that we've looked at here is chapter 6F and chapter 6G. Have a go at it. Good luck. Send me an email if you need any assistance. Otherwise, I'll see you all next week. Have a good one.